Welcome to Lesson 4, Calculating Heat of Phase Changes. Our lesson objectives: determine the effects of intermolecular forces on the heat of fusion and vaporization of a substance, calculate the heat required by a substance to go through a phase change, and determine the changes in energy of a substance. So when do we use our equation Q equals mc delta T for heat calculations? Well, we can only use that on the solid, liquid, and gas only lines on our heating curve here. This is where the temperature changes. There is an actual delta T, a change in temperature. During the phase changes, there's plateau here, and you notice if you go across to the y-axis, which is temperature, there's no change in temperature during a phase change. And so we can't use the equation Q equals mc delta T because there's no delta T. It would be 0, and if it's 0, then all of our calculations would come out to be 0. And since we are adding heat, we know there has to be heat involved in our phase changes. So we have to use two different equations. The first one is going to focus on this first phase change here, going from a solid to a liquid, which is melting, or removing heat, going from a liquid to a solid, which is freezing. And so the equation that we're going to use is on table T, and that is Q equals mHF, where m is the mass and hf is this constant, which is the heat of fusion. And that's the amount of heat needed to change a substance from this solid to liquid or liquid to gas. I'm sorry, liquid to solid. And so this constant listed on table B, heat of fusion, is 334 joules per gram. That means for every gram of water, it requires 334 joules to get it to go through this phase change from solid to liquid or liquid to solid. Looking at the next phase change, going from a liquid to a gas or a gas to a liquid, this is called the heat of vaporization, and the equation is Q equals mHV, where m is the mass and hv is the constant heat of vaporization. So the heat of vaporization is the heat needed to change a substance from a liquid to a gas or a gas to a liquid. And so just like the previous equation, the only thing we need to add in is how much of the substance do I have, and we use m, which is mass, to account for that. The constant heat of vaporization is on table B as well. That's just below the heat of fusion, and that is 2,260 joules per gram. So for every gram of water, it requires 2,260 joules to go through this phase change. What are the effects then of the intermolecular forces on the heat of fusion and the heat of vaporization? Well, if you recall, what is holding atoms or molecules in certain phases, solid, liquid, or gas, are these attractive forces between these atoms or molecules. And so if the attractive forces, in this case the intermolecular forces, are stronger, that means it's going to require more energy than to overcome them to separate these atoms or molecules. And therefore, the heat of vaporization and the heat of fusion is going to be higher due to this increased amount of intermolecular forces. So higher melting point, higher boiling point, stronger intermolecular forces, higher heat of fusion and heat of vaporization. It's also important to note that if you look at the heat of fusion compared to the heat of vaporization, the line is longer, meaning it takes more energy to get through this phase change than it does this phase change. And that's why if you look at the constants, you'll see that the heat of vaporization is much higher than the heat of fusion. It does take more energy to overcome the attractive forces going from a liquid to a gas, because we are essentially almost completely breaking those attractive forces. So let's check your understanding. Can you determine the effects of intermolecular forces on the heat of fusion and vaporization of a substance? So let's see some examples of our heat calculations for heat of fusion and heat of vaporization. So here's one for the heat of fusion. How many joules does it take to melt a 16-gram sample of water at 0 degrees Celsius? So the first thing I need to know is, how do I know which equation to use? Am I using Q equals mc delta T, Q equals mHF, or mHV? Well, the telltale sign is that we see the word melt and we see at 0 degrees Celsius. So for water at 0 degrees Celsius, that's the melting freezing point. That's that phase change. And so that's our telltale sign. We don't see a change in temperature, so it can't be mc delta T. And we're not talking about when water boils at 100 degrees Celsius. And so the strong indication are these two things here, melt and at 0 degrees Celsius. Whenever you see those, we're going to use our Q equals MHF. Now let's figure out our knowns and our unknown. So how many joules? That is Q, and so Q is what we're solving for. That's our variable. We do have our mass, which is 16 grams, and the constant heat of fusion from table B is 334 joules per gram. We're going to plug that into our equation, Q equals MHF, and we get 16 times 334, and so the amount of heat, our Q, is 5,344 joules. If we're going to round to proper significant figures, that would be 5,340 joules. What does that mean? It takes 5,340 joules of heat energy to take 16 grams of my substance and melt it. So in this case, 16 grams of ice, frozen water, and turn it to liquid. Now let's look at an example of the heat of vaporization. How many joules does it take to boil a 250 gram sample of water at 100 degrees Celsius? So again, how do we decode and know which equation to use? Well, we don't see a change in temperature, but we do see the word boil, and we see at 100 degrees Celsius. And water boils at 100 degrees Celsius, and so therefore that's this phase change right here. And so we're going to use our Q equals MHV equation. So again, we're going to list our knowns and unknowns. So it says how many joules, so we're solving for Q, that's our variable. The mass is 250 grams, and our constant heat of vaporization from table B is 2,260. And so we're going to plug that into our equation, Q equals MHV, where M is the mass, V is that constant, so 250 times 2,260 gives me an answer of 565,000 joules. So it requires 565,000 joules to take 250 grams of water in the liquid phase and boil it. Let's see one more example. How much heat is needed to melt ice at 0 degrees Celsius if the sample weighs 255 grams? So let's first figure out which equation we're going to use. So I see the word melt and at 0 degrees Celsius, and so that's indication we are at this phase change here, which is the heat of fusion. So I'm going to use Q equals MHF. I'm solving for how much heat, so that's my Q, which is my variable. The mass is 255 grams, and our constant is 334 joules per gram from table B. Plugging that into the equation, I'm going to get 255 grams times 334 joules per gram, and I get an answer for Q, my heat, of 85,170 joules. And round to proper significant figures, it's 85,200 joules. That's how much heat energy is required to melt 255 grams of ice. Let's check your understanding. Can you calculate the heat required by a substance to go through a phase change? So now looking at the heating curve, adding heat over time, all the vertical parts here, we see that temperature is increasing, so therefore average kinetic energy is increasing, and the potential energy then is remaining constant. On all the phase changes, the horizontal parts, the plateaus, temperature is, as you can see here, remaining the same. Average kinetic energy, therefore, remains the same, and the potential energy, therefore, is increasing. On a cooling curve, which is essentially just the opposite, we're removing heat. For the vertical parts here, we have temperature decreasing, so average kinetic energy decreases, and potential energy remains constant. And all the phase changes, the horizontal parts, we have temperature remaining the same, average kinetic energy remains the same, therefore, and potential energy is decreasing. So the way to remember this is, remember the 3 P's. For the plateaus, which are phase changes, the potential energy is changing. For the diagonal parts, here, here, and here, temperature is changing, so therefore average kinetic energy is changing. So let's check your understanding. Can you determine the changes in energy of a substance? At this point, you should be able to determine the effects of intermolecular forces on the heat of fusion and vaporization of a substance, calculate the heat required by a substance to go through a phase change, and determine the changes in energy of a substance.